Okay, so the next topic of our course is synthesis of one port network, which is LC emittance, right? It's only an LC function which we are learning right now. Thereafter, we are going to learn RC and then RL. So same book I am following, and I am following the chapter number 11. So synthesis of one port with two kinds of elements. So we are going to study one port network. We know what is one port network, right? And we will have passive networks only, which might be RC, RL, and LC. So it's a combination of two will be there. Sometimes it will be combination of three, but what we are studying right now with theory of two scientists called Coyer and Foster. They have given this theory in 1924 and 1926. This is the one of the ancient technique which we are studying, but afterwards you can build up everything on top of this one. And we are going to use only these two elements, either LC, RC, or RL. Yeah. Whenever there is an LC emittance driving point function. By the way, is there anybody who knows what is emittance function? Yes, Aman. Yes, Aman. Okay. Is there anybody else who wants to say? Vaishali, what is emittance function? Hmm? Yes, Aishwarya. Yes, Vaishali, I am talking to you. Okay. Okay. What is admittance function? What is admittance function? Yes, Vaishali, now tell me. What is admittance function? 1 by Z. Okay. 1 by Z of S. Or what is Z of S, by the way? Impedance function. Okay. So now what is emittance? Yes, Ashwarya, you were saying something. Yeah. So combination of impedance and admittance that will form emittance. There might be one more. Do you know about this one? What is this reactance? Yes, Aman. No. Reactance. In your school time, have you studied this? Yes, Manpreet. Huh? No, that's like how to denote X. It's a different thing. Okay, so it's provided by all the like capacitor or inductor, and it's actually something R plus j x of omega, right? Generally, where X is reactance, and all the ideal inductors and capacitors are actually forming the reactance, right? When there is no resistance, but in reality there is a resistance, right? Which is known as the parasitic resistance of an inductor or parasitic resistance of a capacitor. And how you are keeping that either in series or parallel, it depends. So what do you think? If inductor is there, it's a purely reactive element, but if I want to create the parasitic resistance, where should I keep, in parallel or in series? Are you following my question? Yes. These are the fundamentals. Maybe if you forgot, I'm referring same. Yes, Gaurav. I'm saying that inductor is the one which is purely reactive. Reactive is the function where there is only imaginary part. Means the impedance of this one is equal to how much? J omega L. Right? There is no resistive part. It's only imaginary part. Right? So this is not the reality. In reality, there is a resistance in inductor. So will it be in parallel or in series? Series. Okay. if you are looking at the capacitor whose impedance is equal to 1 by j omega c, then where should I keep the resistance, in series or in parallel? By the way, this green colored resistance is a parasitic. In reality we are not connecting, but it's a parasitic is unwanted one, which was there. So all the inductors in reality, they are not purely reactive. It might have some resistive part also. Okay, so where it should be? Hmm? Okay. Okay. This is just for your information. Maybe you must have studied somewhere in your IC 160, right? So these are the functions, right? Aman, you have any doubt now? Admittance, impedance, emittance, and reactance, right? Hello? Yeah. So if you don't have any problem, and if I'm writing Z of S is equal to M1 of S plus N1 of S divided by M2 of S plus N2 of S. Do you remember the notations of M1 N1 and M2 N2? What is M1? Even function, right? M2 is, but this is even of numerator, this is even of denominator, this is N2 is odd of denominator, and N1 is odd of numerator, right? So from that you can find out this. By the way, somebody can tell me what is the condition to become positive real function? So there are three different conditions are there which needs to be checked for positive real function. What are those? Hmm? Pole and zeros has to be at left part of the left side, right? It should not be right side, right? Next, hmm? It has to be Hurwitz. To find out Hurwitz, we are using a technique called, what is the technique by the way to find out the Hurwitz? Hmm? Okay, continuous uh, fraction, right? We are doing. And what is third one? M1 M2 minus N1 N2 has to be greater than or equal to 0. This is the condition coming from the fact that real part of whatever the function you have, I'm writing here z, but it might be y, it might be I, right? Or it might be r, that has to be greater than or equal to 0. These are the things we studied. And if the function is positive real function, then and then you can synthesize. If the function is not a positive real function, then you cannot synthesize. That means that you cannot make the circuit. When I'm saying you can synthesize, means by looking at this impedance function or admittance or whatever function you have, you can draw the circuit. Okay, so there are few terminologies just for completion. Do you know what is the meaning of analysis? This was the first part of our course. If the circuit is given to you, you can analyze it and you can find out how this circuit will respond on time domain or maybe frequency or maybe anything. You want to understand how it's going to be like it's going to work. Second part is synthesis. Synthesis is the one where function is given to you. From the function, which might be IO, or sometimes IO function, or sometimes IO characteristic. Do you understand what is IO characteristic is? IO characteristic is the one, let's say this is the characteristic for an operational amplifier where input is here and output is here. From here you can find out how the circuit will look like from the characteristic. There might be some circuit which looks like this one. you may have a circuit like or characteristic which looks like this one. It might be any like VDS, IDS. I'm not going into it. So from characteristic or the function, you can draw the circuit. That kind of approach is known as synthesis. Right? This is what we are doing right now. And there is one more approach, design the circuit. So what do you think designing a circuit means? It's not design competition of RLC circuit. What do you mean by design? Manpreet, what do you think? Any wild guess? Komal? Generally, this kind of things you are going to study at the higher level. Designing a circuit, let's say. You have to design a circuit. When I'm saying design a circuit, what do you think? Any guess? Okay. So you are saying that transfer function is known to you or the characteristic is known to you. From this, you already made the circuit also, right? You made the circuit. Circuit diagram is available with you. We are also calling diagram is equal to schematic. So both are synonyms. This is available to you, but for given transfer function, there is something on top of this one, which is called specifications. Let's assume that you are designing a filter. I am giving you specification. So this is a characteristic. From this, I can synthesize it and I can write down the transfer function also. What is V out by V in, by the way? In terms of Laplace? 1 divided by S square plus LC. LC plus? Okay, one more time. This is correct? Numerator has only 1 or something else? Yeah? Right? This is correct or not? The function which I wrote. Oh, sorry. I made a parallel combination. Sorry. 1 by CS divided by this one, and it has to be so. Right? 1 by S square LC plus 1. Right? Okay. Sorry. So, in this function, this is a general transfer function. This is a general synthesized circuit. But if I am telling you to design a band pass filter whose frequency response will have, so this is 1 kilo and this is 100 kilo with the amplitude of 20 dB. Let's make this one so that it will become in logarithmic scale. Okay. So if these numbers are given to you and you have to derive the value of L, C or whatever the components available in your circuit, if you are designing that, then that is known as design, where you are trying to meet the specified specifications. For that, you are determining the value of the capacitor, inductor, resistance, or there might be transistor also. Right? So all these things are coming under one class which is called design. So analysis, synthesize, and design. So design you are going to study in maybe next course, whichever you are going to study, either in digital side or maybe in analog side. So in DSP generally people are designing all the filters which are digital filters. Okay, so there is one more thing. From this function you can write down the real part of j omega times I square, and half of that will give you the average power, which is already known to us. One more thing, where I is the input current for a pure reactive network. Now we understand, when we are saying pure reactive network, means it does not have any resistance. It is known that the power dissipated is 0 by this equation, because real part is 0. So it will be 0. Therefore, we can say that the real part of z omega equal to even part of z j omega equal to 0, and already this equation is known to us. To achieve this, we have multiplied and divide this equation by m2 minus n2, and through that we have derived this equation, right? And we looked at the just a real part. Now, to achieve this equal to 0, we may have two possibilities. One possibility says that if m1 is 0, n2 is 0, then the function is 0. If that is the case, when m1 equal to 0, n2 equal to 0, m1 equal to 0, and 2 equal to 0, what are you going to see here? As a part of this z of s, which was the previous one, this one, what you are going to see? m1 equal to 0, n2 equal to 0, so n1 divided by m2, right? The new impedance function will be n1 divided by m2. Similarly, can you tell me other possibility when m2 equal to 0 and n1 equal to 0? What are you going to see at the output? It will be m1 divided by n2. So from here you can say that if you want to achieve a positive real function for a LC emittance function, then the impedance function is ratio of even to odd, or maybe odd to even, might be from any side, numerator or denominator side, that will give you the ratio, right? That's a positive real function. That's previous chapter. Now, you can go through my previous video lecture. Right? There are only inductor and capacitor, what we are studying right now. So last time I told you that there is no unique solution. Whatever circuit you are making, it does not have unique solution. But we are studying a technique through which we will get the unique solution. Still, like, but you have to tell uh, what kind of approach you are applying. Like, there is a Foster 1, Foster 2, Coir 1, and Coir 2. So this Coir and Foster are the one who have found out this approach, and Foster himself gave two different approach, where you are keeping the whole in one you are keeping the impedance function, and here you are keeping the admittance function, and then you are achieving all the impedance in series, and some places you are achieving in parallel. So there is a systematic approach. When we are asking to find out the Foster 1 based circuit, then it will have specific look like this one, and so on. So we'll derive only unique solution given by these two scientists, right? Okay. So now looking at the properties, ZLC of S or YLC of S, we are specifically writing this in the subscript just to mention that this is for only and only LC circuits. That it's a ratio of even to odd and odd to even, right? Since Mi of S and Nj of S are Hurwitz, because if this is not positive real function, you cannot make the circuit using LC. So it has to be positive real function. Positive real functions, all positive real functions are Hurwitz. So if they are Hurwitz, they will have only imaginary roots. And or maybe there is one word which was written as there will be only simple roots which will have only roots on g omega axis. So you cannot have the roots here and there. You will have poles and zeros on g omega axis only, considering the fact that it's purely reactive circuits. We don't consider that there is a resistive part also, but in reality maybe at higher level you will study the fact that there is a resistive part, and because of the resistive or the parasitics you will get some harmonics or some non-linearities. So that you are going to study in power electronics, right? So if there is a function which is as follows, where the numerator has power, degree of 4, and denominator has 5, and when you are you are increasing this, you can see that there is a difference of 2. The example which has been taken, it has difference of 2, and from denominator to numerator you have the degree difference of 1. This is also the case we already studied. If it is unity or less than 1, or you can say that it's 0, then you should try to uh, synthesize the circuit. Otherwise you should not do that, right? Or you will get some wrong answer. Okay, here if this b3 equal to 0, because this is just a case study taken from the book, so he is keeping b3 equal to 0, then I want to find out the roots in the denominator. Can you find out the roots in the denominator if this is b5 s raised to 5 plus b1 s equal to 0? By the way, how many roots can you see for this function? How many roots will be there? Hmm? Five roots. Okay, so what are those roots? Okay, 0. You will tell me 4 different roots. Hmm? They may be same also. They may be same also. You tell me, look, you must have studied complex number. Through complex number, you can find out, no? Yeah. So try in your notebook. Is there any equation which you studied in your school time using complex number? So one root is 0. That's very simple. So this I can write down, right? And so s equal to 0 and s raised to 5 equal to minus b1 by b5. So now, if it is square, you know how to do it. Okay. If there is some n number, there is a direct equation. I don't know whether you remember or not. Or so this is the equation. In such cases, there is the equation. Hmm? Yes. So there will be, with respect to angle, you will have all the values. E raised to j 2k minus 1 pi by 4. Right? So this is the equation through which you can find out all the roots. Right? By the way, what is a okay? Just for, by the way, those people who forgot all these fundamentals which are useful for network theory, there is something called appendix given in the Franklin Kuo book. Yesterday I was reading and I found it's really useful. Like appendix A is linear algebra, B is complex number. So you can read both of them. They are useful, and it will be useful for all the courses, right? So what do you think? E raised to j theta is equal to, in terms of sine and cos, can I write down? Hmm? Cos theta. Okay. Right. Do you remember cos theta in terms of e raised to j and something? What is that? E raised to sin theta. Hmm? Minus, but divide by 2j. Okay, right? So use all these things, right? Because these will be very useful if you are if you are taking DSP course or analog course or anything which is related to electrical engineering. You have to use complex number every day. But if you are into DSP, there is only one thing which can save you, it's complex number. So they are going to use complex number and all these formulas, right? Okay, so it is clearly seen that the S of Sk are even on the geometric axis, thus violating one of the basic properties of an LC emittance function. If you are looking at this, all the okay. So can you comment on the roots of Sk, whether are like what values you are going to get, positive, negative? So 1 minus 1, something like that. Is there any iota and minus iota? Okay, multiply by, yeah, yeah, okay. Sorry, I forgot to consider that one. Okay, so I made any mistake or yes, Sashi? Correct, right? So you will get two real numbers, two real and two which is imaginary, right? You can find out, right? And hence it is violating one of the basic rule of LC emittance function, which says that you should have all the roots lying on, it might be pole or zero, all has to be on j omega axis. Just to realize one thing, it might be either inductor or capacitor, because the impedance of inductor is equal to j omega L, and impedance of capacitor is 1 by j omega C. So this is only possible when all the roots are only on j omega axis. If they are not, then you cannot realize LC impedance function. It might be anything else. If it is where, or even he wrote in English, it's even, not odd and even. Okay. So he is Italian. Look, Franklin Co is Italian, right? Even I got confused, right? So there are some of the mistakes in his English also, or when he is taking the notation of units. Like he is writing Faraday is F and Henry is H, but it is wrong notation. Okay, please, when while reading Franklin Co book, which is very good book, but there are some problems, right? This F is not equal to F, but this is, if I am writing in small letter, it's equal to 10 raised to minus 15, which is equal to femto. But F in capital is equal to Faraday. H in capital is Henry. Right? Anyway, so let's have some general LC driving point function, which is saying that you may have k divided by s, or you can have k times s and then rest of the transformation. Means at the origin you can have 0, or you can have pole. When at origin you have 0, means it says that inductor will be there at the beginning, and thereafter rest of the things will be in shunt in series with that. If pole is available at origin, means capacitor at the first element and rest of the things are in series because other things are z of s we are going to write down in terms of the first element, let's say in this case k divided by s, and then rest of the things I am going to find out by partial fraction method, right? So all the things, if I'm writing for the impedance function, then they will be in series. If I am writing same thing for y of s, then all these things will be in shunt, and the first element will be inductor if it is admittance, right? So you need to look at the things how you are formulating your transfer function in your way, right? So till now still there is no unique solution. Okay, we have not learned to get the unique solution right now. Still it's solution which will have just inductor and capacitor, that's the only thing. So you have to make a transfer function which looks like this one. We are doing this for the one reason, that you have one by, the reason is when you have such kind of network, you are going to see 1 by s square lc plus 1, right, which looks like this one, right? There might be some k actually, I should say k. There might be the case if it is inductor and capacitor in parallel, then what do you think the uh, impedance function will look like? You can find out in your notebook. When inductor and capacitor are in series, right? So still you will have function which looks like this one, but the numerator will have some extra zero, right? So you can find out that. But if this is the case, and if I want to draw the circuit which is not going into series but into shunt, then I am going to make a partial fraction such a way that I am going to get something like first one was k1 by s, then second has to be k2s divided by s square plus omega 1 square, then k3s s square plus omega 2 square. This going to give me this thing, like for both. And all these shunt elements will be in series because this is z of s, right? Can you see the system? So if you can see that, then there might be like one way of writing the LC driving point function as k0 divided by s plus rest of the things, but they have written which is having inductor and capacitor in shunt. Each of these element is actually going to give you inductor and capacitor in shunt, where like these polynomials can be found out by the value of L and C, right? Which is the design part, right?
K naught by S is capacitor.
K naught by S,
Capacitor.
it's
Capacitor.
it's a capacitor. Yes, right now it's a capacitor, but this is a general equation where author has thought about one condition, but there might be other condition which looks like this one, and you may have this one also. So there are two kinds of transfer function. You need to check which side is higher, numerator or denominator. If numerator is higher than denominator, then you are going to have inductor as a first element. If denominator is having higher degree than numerator, then you are going to have capacitor as the first element, right? And then rest of the things you can find out. But you can see there is an extra element which is k infinity. So what this element says, you if you have 0 at origin here, sorry, pole at origin, and as we have agreed that the difference between numerator and denominator will be 1, difference with the degree will be 1. If it is like the numerator is higher, then you will have more number of zeros than poles, and the difference will be again 1. If this is the case where numerator has higher order or higher degree than 0, then the difference will be 1. And you can say that just to balance this, we are going to add either one extra pole or extra 0, which will be at infinity. This is going to be decided by the fact if you have pole at origin, you are going to keep 0 at infinity, which is available very far. Just for mathematical balance, we are doing this, right? Are you following this, or do you want me to repeat anything? Hmm? Okay. So what I am saying, if there is a transfer function, so there are two possibilities. So there are two possibilities. That one possibility says that the numerator has higher degree than denominator, or another case, numerator has lower degree by denominator, and these two difference will be always 1 or maybe 0, right? This will be the case. If you are seeing that the first case, which is numerator has higher degree, then you are going to see inductor as first element, or you can say that there is pole at origin. Can you see this? You find any difficulty in the first part? If no, then the second says that if the numerator has degree which is n minus 1 and the denominator has degree which is n, then what we can say? What will be the first element? In this case, capacitor will be the first element. Rest of the things might be in series or shunt depending on how you are making the partial fraction. And hence we can say that there is 0 at origin. Few more things we can add here. We can say that in the first transfer function, if there is pole at origin and numerator has zero at origin and pole at origin. So if 0 at origin, I can say that there are, if n number of zeros, then there is n minus 1 number of poles. Just to balance this exactly n number of poles and n number of zeros, I am going to add one more pole which is going to be available at infinity. This is only one thing I am going to do. Similarly, there will be n minus 1 number of zeros and n number of poles. Just to balance this condition, I am going to keep 1 0 at infinity, right, which is available at very far. Okay, so we are doing this to draw a reactance curve. This is our agenda. Otherwise, it is not required. To know that how the reactants behave with respect to different frequency, because even though you have n number of poles and n number of zeros, you might have n number of poles and zeros and anything you have, but still this frequency, rather than drawing this, let's draw the Bode plot where so this is frequency with respect to magnitude in dB. So there might be some poles and zeros, but still this whole frequency response is not getting over here. It's available till infinity. So I can say that there might be some at infinity zeros and poles are available. But in Bode plot, I don't need to know whether it's pole or zero. But for our case, we should know whether it's poles or zero. That we are going to understand when we are going to draw the reactance curve. Okay. But right now, understand that we need to keep something at infinity, and that something is depending on what is available at origin. If at origin 0 is available, you have to keep pole. If pole is available at origin, you have to keep 0 at infinity. Right? Okay. Because just after next slide we have to draw the reactance curve. So what this z of s is of second type of transfer function where poles are more than 0 and that number difference is 1. So there is availability of pole at origin, which is k0 divided by s, and as already we agreed, I am going to make a circuit which is going to have each component will be the combination of inductor capacitor in parallel, right? So all these all these functions, small functions, which I can call them as z2, z1, z3, all z2, z3, z4, all are the shunt combination of inductor capacitor. Z1 is right now pole at origin, means you will have a capacitor. As I told you, if you have pole at origin, we are going to add one extra term at the end, which is k infinity times s. This is going to give us 0 at infinity. This will help us. This will help us to draw reactance curve. This is the only thing.
It is giving 0 at infinity.
It may be 0 or pole. Anything can be there, right? If something is available at infinity, which might be much beyond your UGBW, then it's whether you are keeping 0 or pole, it doesn't matter. You can keep anything. It may have infinite number of poles and infinite number of zeros available at infinity, which is beyond your interest.
But sir, this k into s, how it is giving at 0 and infinity? Like for a 0, z of s must be equal to 0 at s equal to infinity.
So I'm saying there is one more extra term which is k infinity s. I'm just saying just to adjust mathematically.
So at s is equal to infinity, the z of s must go to 0, na?
Yes.
So
Yes.
k of infinity, should be very very small. That implies this thing, na?
K infinity is equal to not. Yes, k infinity.
Because other terms will become 0 already.
Yes, k infinity has to be very small. Okay.
It
Okay.
should be 0 only, na? For
Just for okay, if you want to keep it 0, it's k infinity tends to 0. Now you like it, right? Okay. This is just a mathematical formulation in general. That's why this has been kept this way. It might be like what you are saying is correct. K infinity tends to 0. I can keep it. No problem. So if I'm writing just something in terms of j omega, so this is equal to j times minus k0 divided by omega. That's the first term. Second term is equal to 2k2 times omega. J is common and going outside, and this is equal to omega 2 square minus omega square, and we can write down similar terms till end, and this is k infinity times omega where j is taken common at the right, and we can write down z j omega is equal to j times x of omega, where x of omega is reactance, right? And one more thing, if I am interested in finding out the slope, I'm interested in finding out the slope. If I'm interested in finding out the slope, what I'm going to do, I'm going to take the derivative of this reactance with respect to d omega to find out the slope. So this is the slope of the reactance curve. So this is going to give me k0 divided by omega square and so on. You know how to differentiate, right? And this is the important term which we need to find out, which is saying that for all the residues, we understand all the residues are these entries k0, k infinity, k2. With whatever technique you are finding out, this is known as residues. And if you forgot, please follow something called residue theorem as a part of complex number. Okay, right? Because in previous surprise quiz, I realized some of the people have problem in understanding residue, right? Residues are k0, k infinity, k2. By the way, how do you find out residues? Then by keeping the mathematical values and all, or okay, you are not taking a limit or something. It's come similar, but okay. So whatever you feel that giving you the fast answer, you follow that. Otherwise, through residue theorem, you can keep the limit at whichever place you want to find out the residue. Here it's at origin, so you have to keep omega tends to 0 and you can find out k0 for the entire transfer function. This is the way to find out. So you can follow whatever the method you like. You can revisit it, which is given in the appendix number B, to learn the residue theorem. It's very easy. In appendix, it's not complicated things, it's just repetition. But still, if you think that it's complicated and if you are not able to find out, please talk to me. I'll try to cover in between somewhere, right? But now most of the people are able to find out these residues, right? Just you didn't know the word residue. So this is going to be known as residue, and remember it forever, right? So residue ki are positive. It is seen that for any value of LC function, this slope also has to be greater than or equal to 0. Okay. So this is just one theorem which was derived by this book. That's why I'm showing here. Otherwise, just drawing a reactance is very easy. Anyway, so let's have one example. Before we go today, we have one example. So this example is different than what we have derived the equation earlier. So what this equation says, this has more number of zeros or poles. Poles are more. One more than zeros, right? However, you have 0 at origin, right? You have 0 at origin, by the way. And you can write down this as j k omega and replacing all this Laplace operator by j omega, and you can have this equation. Now I'm interested in finding out how this x of omega will behave with respect to frequency omega in radian per second, right? So by looking at this transfer function, can you tell me what is going to the function will look like? Can you draw x of omega? You may have following things, which is going from 0 to infinity. Remember, we are not going to draw anything less than 0 because we are only drawing the system which is causal. If it is non-causal, we are not going to touch that, right? So x of omega from 0 to infinity, where x-axis is omega in radian per second. So what is going to happen at 0? Okay, so it will be 0. Then what? So okay, for keeping the things easier, we have omega 2, omega 3, and omega 4, as well as omega at infinity also. Right? Just to complete this whole diagram, I kept one extra term also. Okay, so what is happening at omega 2?
omega less than omega
Infinity. So, but just to find out, it might be possibility that it might be plus infinity or minus infinity. How did you find out it's plus?
for omega less than omega 2. Like
Hmm.
when it is approaching omega, it will be plus.
Hmm.
When it is moving away from the omega 2,
Hmm.
then it will be minus.
Okay, so you are looking at this equation
Yeah.
and keeping the value at omega when omega 2 is more or omega 2 is lesser. Your omega is moving from this side to this side. So when omega is lesser, this term will be actually becoming bigger one, right? And so on. You can find out this, right? So from that you can find out this will be positive sign. So when you are moving from 0 to omega 2, you may have something which is going infinity, right? There is something called asymptotic line I am drawing here. Asymptotic line will tell me that at infinity, this is going infinity, by the way. Uh, this dotted line is going towards infinity, and right now it's in parallel of that, but at infinity this function is infinity. Okay, so what next if omega 2 is lower than omega?
Minus.
Then it's minus infinity. So this was the region when omega 2 was higher than omega. This is the region when omega 2 is less than omega. Then this sign is become plus to minus. So it will just next to omega 2, uh, some omega 2 plus region which is little bit higher, you are at minus infinity. And what is happening at omega 3, by the way? Omega 3 is 0, by the way. Omega 3 is 0, or 0 frequency is the one when the function becomes 0. Infinity is the one where function becomes infinity. Right? 0 does not have any problem because this is 0. This at infinity is 0. The problem occur where you have to find out whether you are getting plus infinity or minus infinity. For that you need to look at the slope, and through which you can find out which side you have to move. So this is 0, but this side it is minus infinity. So this is coming from minus infinity to 0. As omega 3, like you are leaving the place which is omega 3, then you are going at plus side, and you will go at plus infinity at omega 4. But when you are leaving omega 4, means if your omega is greater than omega 4, your frequency will have x of omega which is minus infinity, and at infinity it will go to 0. Otherwise it's not going to 0. So this x of omega gives me information that what is happening to your system at infinite frequency, whether it's bounded to 0 or bounded to somewhere outside. This might be useful for finding out even the stability sometimes, although it's not part of this course, but you can use this theory for your next course, which is control theory, right, where you can use these reactance curves. Maybe rest of the things we'll talk maybe next time. By the way, this Thursday do we have assignment exam, Akshita? Right? So 2-port network assignment exam, okay, as decided on Thursday.